Hello, hey, in this video we're going to look at the truncated normal distribution. And one of the reasons I'm doing this video is I'm doing a little series on EM algorithm, and I wanted to do linear regression with right sensor data and use the EM algorithm in that setting. And there's one little tricky part that requires the knowledge of truncated normal data. And so instead of putting this in that video and making it really long, I'm creating a new one, and then we'll reference back to this. But a truncated normal data means that we have a just a normal distribution, but then we restrict it to an interval. And these could be negative infinity or infinity. And so it's f of x restricted to some interval. And the density for that is just f of x, which is the normal density, normalized over cap f of b minus cap f of a. And this is an indicator function that indicates that it's 1 when we're between a and b and 0 otherwise. We can also, this is the one-sided truncated, so we're less than, where x is greater than a certain value. And this is the setting that I'm going to show in this video because it's relevant to the video in the EM algorithm that I'm doing. So this is the density for a truncated normal distribution where x is greater, given that x is greater than c. And so we will find the mean and the variance and the expected value of x squared. All right, before we start though, let's cover a few notes here. Note that the derivative of a normal distribution is you get your normal density back times this constant. Okay, and this is when f is normal. So we're going to make use of this to shortcut much of the algebra. The good old fundamental theorem of calculus, that if you have the derivative of a function, then the integral of that ends up just being the function evaluated at the endpoints, and then the survivor function, which is 1 minus cap of f. So this is the cumulative distribution function, and then 1 minus is greater than that, probably the x is greater than some value x. So the expected value, this is what we want to find. By definition, it is just plug in x times the density integrated over all possible values. And so nothing new here. Well, the survivor function is constant in regards to x, so it can be brought out front. And then we're going to look at this. Well, this right here, we're going to try to make use of this property, but we have to add and divide by some things to get it into that setting. So that's what this does. And going from here to this step is just algebra. You know, so we take this and then we subtract the mean. So that means we have to add the mean if we're going to subtract the mean. And then since integrals, you know, the integral of a sum is the sum of integrals, then you can take that in and isolate that by itself. And then here you divide by sigma squared, multiply by sigma squared, then you also need a negative in there. Okay, and so that, I'll let you show that on your own, but it's literally just simple algebra. So here, we'll look at this one. The probability that we're greater than c is this piece here is cap f of c, which cancels with that and leaves only mu. So here, this is the property that we discussed. This is the first derivative of a normal, and then everything else is the same. And then we can use the fundamental theorem of calculus here and evaluate the integral at the limits. And now this is, as x goes to infinity, you know, and that this is 0, and then that is just f of c. So this is 0, so then that negative makes that positive, and then I like writing the mu out front, and then we just have sigma squared times f of c over capital S of c, and that's the expected value of x for the truncated mean. Now, the expected value of x squared, by definition, is this, and then we're also going to use the first derivative trick again, and then we're going to separate that into x times x, and then we're going to subtract the mean divided by the standard, or the variance, and again, going from here to here is algebra, and so I'm going to leave that step to you. But here, you know, we subtract it, and then we have to add it, and then we divide, so we have to multiply, and there's a negative, so we take the negative. So that's this to this. Well, this piece here is, we just solved that in the previous page. That's the expected value of x squared. Okay, this right here, this piece, that's the first derivative. So we'll replace it, and then we have x times it. So when we go to the next step, we simply, you know, replace this with the expected value of x, and we still have the mu constant. And then here we have the first derivative, and then the constant out front. Well, here we're going to use the u dv substitution, integration by parts. Let u be x and dv be f prime of x. And then we get this. And then we multiply that in to get this, and we evaluate it here, and evaluating this at infinity, it goes to 0, and then it's minus evaluated at c, and this here is just capital S of c. Then we multiply this in, the 0 of course goes away, the negatives become positives, and we get this. So this is just sigma squared, and then we get this times that, which is that. Bring this down, and then just simplify it. I like to bring the mu squared plus sigma squared, and then factor out an f of c divided by kappa c. So that's the expected value of x squared. And the variance, and then is literally just the expected value plus the expected value of x squared plus expected value of x quantity squared. Plug in the values, and then you get this. And I'm not going to try to simplify it because I don't really need it for the M algorithm, linear regression with right censored data, so I'm not going to do it here. I hope you enjoyed it. If you like it, please like it, subscribe so you don't miss the next one, and I will talk with you later.